The most powerful example of exponential functions is compound interest. When you get when interest is accumulating not just based on the original amount, but also based on the interest that has already accumulated. So the formula for compound interest is written here. This is A stands for amount, um, and you can think of it as the final amount. The final amount is based on the amount that you put in, obviously. So this is called the principal. That's the original amount. And and that is being multiplied by, well, this is 1 plus our interest rate. So the 1 represents us keeping the amount that was already there, and then this is our interest rate divided into pieces. So this is our interest rate. This is our annual rate, um, and we want to write it as a decimal. So if we have 10%, we would say 0.1. If we had 15%, we'd say 0.15. If we had 3%, we'd say 0.03. N is about how often we compound it. So compounding frequency. So if we're compounding just once every year, then that's n is going to be 1, and we'll just have 1 plus r to the t. But if we're doing this twice a year, semi-annually, that would be n is 2. If it's happening every quarter, then that would be n is 4, or we could have n is 12, or it could be more often than that. Lastly, t is time in years. You could theoretically have it be in a different amount, but you pretty much always have time in years. So this is our formula. Know it, love it, and let's use it. So if you borrow $13,000 from the bank and they charge you 15% interest compounded monthly, how much do you owe in 3 years? So how much do you owe is going to be our question. We want to know what A is. So A equals P times 1 plus R over N to the nt. So we can go through this question and see what we have. We start by borrowing that amount, so this is P. We are charged 15% interest, so that's our interest rate. Compounded monthly, that is, N is going to be 12, because there are 12 months in a year, so it's happening 12 times a year. And T is going to be 3 years. So let's substitute that all in. A equals 13,000 times 1 plus, so this should be written as a decimal, 15%. N was 12 to the 12 times 3. The long way of simplifying this is to do this division out. But I would say at this point, because we're going to be raising something to the 36th power, this is definitely something that you want to use a calculator for. And when I typed it into a calculator, I got $20,331.27. That is approximately how much you owe in 3 years. So if you're given all the information, you plug it in, solve, and it's pretty straightforward. I could give you A, R, N, and T and ask you for P or any other combination of things. However, sometimes the compounding gets more and more frequent, and mathematicians have a way of expressing what happens if we're compounding every moment, compounding continuously. What happens is that as n gets closer and closer to 0, this part of the expression hits an asymptote. It gets closer and closer to the expression e to the r. So that's a really weird thing, that it always gets closer and closer to e to the r. But if you type this in with a particular r value, you will get an asymptote at e to the r. So what this whole thing simplifies to is a equals p times e to the r to the t, or a equals p times e to the rt. Now this is happening only when n gets closer and closer to infinity, that we can write it as the simpler expression. But this is also something that you should have memorized. Continuously compounded interest is a equals p times e to the rt, or I've heard people just call it PERT. A still means the amount. P is still the principal. E is Euler's number, approximately 2.718. R is your interest rate per year, and T is time. And you can use this anytime that something is being compounded continuously, rather than the previous problem was every month. So what would it be if we did this continuously? Well, A equals P times e to the r. So that's once again going to be written as a decimal, 0.15 t. So 13,000 times e to the 0.45. When we do that, 13,000 times e to the 0.45 is approximately $20,388.06. So there's not a huge difference between compounding continuously and compounding monthly. This is $331 versus $388. There is a difference, and it can't get more than compounding continuously, unless, of course, you change the other parts of the problem, unless you change how much money you borrowed, or how long you borrowed it, or the interest rate. That's compound interest.